Okay, so now that we've gotten some of the background stuff out of the way, right? So some of the stuff that's like, how do we talk about ionic compounds? What are ionic compounds? How do they look? Those ill-defined molecules. We talked about how to determine the charge on a metal cation. I think now we're finally ready for naming. So again, remember, anytime you see a metal or an ammonium ion in your name or your chemical formula, you have an ionic compound. And when we're naming ionic compounds, we basically write what we see with an addition of the charge if we have a varying charge cation. So what are some more exact steps that we can move through to look at this process, okay? So the first thing that we have to do always when we're naming ionic compounds is to determine the cation. It's always written first, whether it be the chemical formula or whether the name. So determine the cation, that positively charged ion, okay? So there are three possibilities for what our cation might be. It might be ammonium, it might be a metal with a known charge, or it might be a metal with a varying charge. So we've got three different things we have to do in that case, okay? So if we see ammonium as our cation, we just write, boom, the word ammonium down. That's all we need to know. It tells us exactly what we need, ammonium. If we see a metal cation that has a known charge, to write down the name of that, you just write down the name as the metal cation. So this is going to be the same as the elemental name from the periodic table. So Na plus ion is called sodium or sodium ion. Ca2 plus ion is a calcium ion. So we would say sodium if we saw sodium. We would say calcium if we saw calcium. Any of those lists of those alkali metals, the alkali earth metals, scandium plus 3, aluminum plus 3, zinc plus 2, silver plus 1. Anytime we see any of those, we're going to follow B here. It's a metal cation with a known charge, and we're just going to write down the name. However, what's interesting that happens is when we have a metal with a varying charge. So if we see that metal cation, it's not on our short list of metals that have a set charge. It's on a list of metals with varying charges. It's everything else, right? So if we don't see one of those metals that we can easily identify, so step A, you would identify ammonium. In step B here, it would be if you had a metal cation that we recognize as having a set charge. If neither of those cases are true, you have a metal cation with a varying charge, and you best be telling me what the charge on that cation is. So if you have a metal cation with a varying charge, you write the elemental name from the periodic table, and then you write Roman numerals in parentheses to denote the charge on one metal cation, okay? So remember when we were calculating those charges on copper? Cu2 plus would be written as copper 2. Cu1 plus is copper 1. Fe3 plus is written as iron 3. Okay, so the idea here is that they're separate compounds. They have separate things that they do. They are involved in different ways, okay? So we have to denote the charge so we know exactly which one of the ions we have. So again, we had copper sulfate, which is copper 1 sulfate, or Cu2SO4 is copper 1 sulfate, or CuSO4 is copper 2 sulfate. These are two entirely separate compounds. They have different properties. That's why we have to tell them apart. If you just said copper sulfate, that does not tell me enough about your metal cation. I have no idea which compound you have if you just say copper sulfate. It's not specific enough. If you said copper sulfate, it could be copper 1 sulfate, it could be copper 2 sulfate. I have no idea unless you tell me. So you have to be explicit when naming your compounds. You have to be sure you use those Roman numerals with parentheses if you have a metal cation with a varying charge, because we want to be certain that we know exactly which compound we're working with. Imagine if one of these was deadly and one of them wasn't, and I just said, okay, get the copper sulfate off the shelf. That's awful. That's not how it works. You have got to be sure that you denote the charge on a varying cation with Roman numerals in parentheses at all times, okay? So the only time you don't use Roman numerals in parentheses is if we already know the charge because we agreed on it and it's one of those cations with a known charge that's on our list. If not, you have to use those Roman numerals in parentheses, okay? Step 2 in naming an ionic compound is dealing with the anion. So step 1, deal with the cation. Step 2, deal with the anion. Makes sense. So we write the name of the cation with those Roman numerals in parentheses if we need them, and then we write the name of the anion, okay? So we have 2 different cases that we might have for an anion. We have 2 different kinds of anions we've seen. We've seen monatomic anions with 1 atom as the anion, the 1 charged atom, or we've seen polyatomic ions, okay? So, we need to figure out if we have a monatomic anion or a polyatomic anion, okay? So, if it's a monatomic anion, you just see one of these names down here in your chemical formula. You just see one of these written, not as a polyatomic ion, because you should be able to identify your polyatomic ions. If you don't see a polyatomic ion, you see just a singular kind of atom sitting there, you must write the anion name of that atom, okay? So I mentioned this before when we were talking about fluorine and fluoride in the video where I gave you a little bit of a warning about naming. This is that moment, okay? So the anion name of these compounds is not what you see on the periodic table. So yes, the ion name is the same for the cations, but it's not the same for the anions, okay? So if you want to write the name of the anion, you have to use the base name of the element with the IDE suffix. So this is the difference between fluorine and fluoride, okay? Fluorine, fluoride, chlorine, chloride. So sulfur, sulfide, okay? So they might have a little bit of a different bit from their base name that they get. Their base name might sound different, like oxygen, sulfur, nitrogen. However, in the end, you have to be sure you're using the base name with the IDE ending. So if you tell me calcium fluorine, I'm not going to know what you're talking about. I assume when you say fluorine, you mean F sub 2. You mean F with a subscript of 2. You have the diatomic element when you say fluorine. However, I know what you mean when you say you have calcium fluoride, okay? Fluoride is the ion, so I'm assuming you mean F minus in that case, okay? So you have got to be careful and use those ion names from here on out when we are actually referring to ions, okay? So again, you write the anion name. So this is not what you see on the periodic table. You have to use the ion name if that's what you mean. And it's the base name that you can see here with the IDE suffix attached, okay? We'll get used to using these. They kind of become second nature. I wouldn't say you have to, like, memorize them. However, you have got to know that these are the base names so that you can properly write down your anion name. Just a side note. Okay? So that's what you do if you have an anion that is monatomic, that does not have more than 1 atom in its ion, okay? These are our regular straightforward ones that we usually deal with, okay? You write the base name with the IDE suffix attached to the end. However, if you got a polyatomic ion, it becomes much easier. We already know the polyatomic ion name because it's just the name of the thing we have. So if you see a polyatomic ion, you just write the name of the ion. So if you see something like calcium sulfate, okay, calcium sulfate. You just write down sulfate. So you don't have to go through this whole ending changing process when we're talking about polyatomic ions. That only happens if we have a monatomic anion, okay? So, to summarize, you write the name of the cation and you put the charge as Roman numerals in the parentheses if need be, and then you write the anion name. So while there's a whole bunch of steps, there's a whole bunch of subcategories here. Really, you look at the cation, determine the name of the cation, You write the charge in Roman numerals if you need it, and then you look at the anion, determine the name of the anion, write the name of the anion. Okay? So that's what we need to do when we name ionic compounds. I'm going to work through some here. I'm going to explain the naming process with you, and then I'm going to give you some to practice on your own. Okay, so now that we've kind of talked through the process of how to name ionic compounds, let's work through some examples so that we can kind of apply these rules like real time and see what we mean, okay? So the first compound here, we want to know what the name of it is. It's listed as NaBr, okay? So if I look at that chemical formula, the way that it is listed, I can see right away, Na, boom, that's sodium, that's a metal. I know for a fact I have an ionic compound. All right, let's keep investigating. So I see that I have sodium, and I see that I have Br, which is bromine, okay? So I've got sodium and I've got bromine. Now I need to figure out what a compound is named that contains sodium and bromine, okay? So I'm gonna follow my ionic naming rules. So if I have sodium, I know that that's an alkali metal, and I know that the charge is always +1. So sodium is a metal with a set charge, okay? So if I have a metal with a set charge like sodium, I just write down sodium, and I don't need any Roman numerals or parentheses. Technically, if you put the Roman numerals and parentheses there, it's wrong, because you don't need them. That's not how we name this compound. We don't have to denote what the charge is because we know sodium always takes a 1+ charge, okay? So if I want to name this compound, I see that I have sodium, a metal cation with a set charge. It does not vary, no varying. So I just write sodium to mean my cation. Easy enough. Well, once I've done the cation, I gotta name the anion, okay? Well, my anion this time is based on bromine. So I have to decide, is it a monatomic anion or is it polyatomic? Well, when I look at Br, it's only just one atom. Mono, one, atomic? It's monatomic. It's just one bromine atom, okay? However, remember, it's not just a neutral bromine atom. It is a bromide ion, okay? So again, you have to use that base name with the IDE ending to name your monatomic cations, or anions, okay? So monatomic anion needs that IDE ending. So here, bromine becomes bromide. We have sodium bromide, sodium bromide, sodium bromide, sodium bromide, sodium bromide. It's late at night, guys. So anyways, sodium bromide is going to be the name of our compound. So again, sodium bromide. Sodium has a set charge. We just write its name. Bromine has the base name of BROM. We add that IDE ending. We get bromide to say sodium bromide. All right. Let's do the next one. Okay. So the next one here is ammonium. I almost said the whole name. Can't really ask you guys to name it if I tell you the name. So this one, we see that we have this ammonium ion, and then we have a chlorine atom, okay? So we got ammonium ion, chlorine atom. So in that case, we look at it. We see that there's ammonium. If we see ammonium or a metal, we know we have an ionic compound, so just triple checking. I didn't trick you. It's ionic. So if I see ammonium as our first ion, I have NH4, okay? I see the NH4. I know that's ammonium. What happens if we have ammonium? We just strictly write down ammonium. Cation taken care of. You write down ammonium. Well, we now look at the anion to determine if it's monatomic or polyatomic, and then we can handle it from there. So I have just one chlorine atom here, so I have one chlorine atom. However, we know that that actually is a Cl minus, balancing out the NH4 plus. So Cl minus, NH4 plus, balance each other out, charge neutral, ionic compound. Cool. Cl minus ion. Remember, it's not chlorine. It is now a chloride ion, chloride. So again, you take the base name of the element and you add the IDE ending. So here we have ammonium chloride, ammonium chloride. So again, if we see ammonium as our cation, we just write ammonium. And then we take care of the anion. In this case, again, we have a monatomic anion. So that means we have CHLOR for chlorine. Then we add the IDE ending to get chloride, okay? So ammonium chloride is the name of our compound. Okay, so we're going to do the third example here. We're going to look at this compound right here on number 3. We want to know what the name of this compound here is. So I take a look at it. I see it's got a metal. It has magnesium at the front of it. I know I've got ionic compound. So I'm going to continue along my ionic compound naming schemes, okay? So we're going to deal with the cation, deal with the anion naming second. So first and foremost, I look to my first element, my cation, and I see that I've got magnesium. Magnesium is an alkaline earth metal. That's the second column on the periodic table, of course. So therefore, we know the set charge of magnesium is 2+. We can just write down the name magnesium. So magnesium has a set charge, write magnesium. And then we look to our anion. We decide if it's monatomic or polyatomic. Here I see that I have the acetate ion. So I just write the name of the polyatomic ion. So therefore I have magnesium acetate. Again, these are all pretty straightforward. It's just weird when you got to figure out the charges. Then you got to remember that the anions have the IDE ending. But those are kind of it. Figure out the charge, remember the IDE ending. So again, here we have magnesium acetate. So magnesium has a set charge, so we only write magnesium, no Roman numerals. And acetate's a polyatomic ion, so we just write its name, acetate. So magnesium acetate. All right, last example. So we have a compound here that contains iron atoms and a compound here that contains oxygen atoms, okay? So what we need to do is determine the name of this compound. As I'm looking at it, I see that I have iron. Iron's a metal. I have an ionic compound. I can continue on my ionic compound naming schemes, okay? So remember, we have to deal with the cation first, and we get information from the anion about the charge on our cation. So in this case, I see that oxygen is going to be what my anion is. We know that oxygen always takes a 2- charge. So if oxygen takes a 2- charge, and I have 3 oxygens, that means I have 6- as my total charge, okay? So 6- is my total charge here. Each of my oxygens gives me a 2- charge. I have 6- as my total, which means I need 6+ to balance it out. So 6- to 6+ to balance it out. So my total amount of positive charge is 6+. However, if I look at that chemical formula there on your screen, what I see is that iron actually has a subscript of 2. So in this case, when we see that subscript of 2, that entire amount of 6 positive charge has to be evenly divided between my 2 iron ions, okay? So I take my total amount of charge, 6+, and I divide it into my 2 iron atoms evenly. So I would say each iron atom therefore gets a 3+ charge. I took my 6+ total charge, I divided it in half because I have 2 iron atoms. So therefore, the charge on each individual iron is 3+. My 6+ total divided by the number of atoms I have of that thing, which is 2. So each iron atom has a charge of 3+. So we write iron, parentheses, Roman numeral 3. So we don't write the Roman numeral 6. We're not denoting the total amount of positive charge. What the Roman numerals denote is just the charge on one of that ion, okay? So each of our irons is a 3+ iron to make up our entire 6+ molecule, or 6+ positive charge, okay? So to make up our entire 6+ positive charge, we need each of our iron atoms to have a 3+ charge. Okay, so that means we write down iron, parentheses, Roman numeral 3, and then we have to determine our anion. So in this case, our anion is only a single oxygen. It's not a polyatomic ion that we recognize. So therefore, it's a monatomic anion. So we name it with the anion name. You take the base for oxygen, which is ox, and you add the IDE ending, so we have oxide. So here we have iron 3 oxide. Again, iron has a variable charge, so we need to go through all the steps to determine the charge. We figure out that iron has a 3 plus charge, so we write iron with parentheses 3 in Roman numerals, and then we have oxide. So iron 3 oxide is the name of our compound there. So I have left you with those examples. I'm going to leave you with these practice problems here so you can see the solutions of all of these in your PowerPoint. But please, please, please go through, do some practice. I've given you some opportunities to practice here. You'll have some opportunities to practice on the homework because you got to have this down pat for the next exam. So our Unit 2 exam, you have got to know how to name ionic compounds, okay? Okay, so now that we've spent some time naming ionic compounds, we also need to make sure that we can go the other way so that we can take the chemical formula or take the name and actually write out the chemical formula from the name. So there's just a couple of quick things we need to remember. We'll walk through the steps. We'll do some examples. I think personally it's much easier to go from the name to the formula of the compound. However, if you have a different opinion than me, that's perfectly fine. So in this case, remember, I'm going to say it 1.5 million times, and I'm going to continue. The overall net charge on an ionic compound is 0. We always have to have charge neutral formula units, okay? So that chemical formula has got to be charge neutral. So when we write the name, so we write the chemical formula of the name of a ionic compound, we have to be sure we have enough positively charged ions and negatively charged ions to balance each other out. So if necessary, we can kind of increase the number of each ion we have. So we might need another positive charge. So we say, okay, add another sodium in, that's fine. Or maybe we need to increase the number of copies of a polyatomic ion we have, right? So earlier, when we were talking about polyatomic ions, we saw magnesium nitrate, and we saw that those parentheses told us we had 2 copies of the NO3. So remember, you got to use parentheses to increase or decrease the number of copies of a polyatomic ion. But basically, when you write the chemical formula of an ionic compound, you look to the name to determine what you have, and then you balance the amount of charge you have so that you have the same number of positive as you do negative charges to create that overall net charge on the ionic compound to be 0. So what do I mean? So the steps you need to take when writing the chemical formula of an ionic compound is first and foremost, look at the cation and determine its charge right away. So, useful information is contained in the name, and this is why we put the charge in the name, okay? So, if it's ammonium, you always have a +1 charge, so you know your cation, you know the charge. If you have a metal with a set charge, you know the charge, move on. However, you do have the varying charges, but they're given as Roman numerals. So remember, the Roman numeral represents the charge on 1 copy of the ion. So one of the ions has that charge when you write the name down, okay? So the first thing you do is you determine the cation and its charge. And then the second thing you do is determine the anion and its charge, okay? So anions always have set charges. We know what to expect with them. It's going to be our monatomics that we're familiar with or our new polyatomic ions. So you determine the cation, its charge, you determine the anion and its charge, and once you've done that, you just need to make sure you have the same amount of positives as you do negatives, and you use the subscripts to increase and decrease the number of each ion you have. So the one thing you have to remember here is that you have to take the smallest whole number ratio. So in your head, you might be trying to balance things, and let's say you come up with something like Na2Cl2. Well, you could simplify those numbers down to just NaCl. So you could divide both of those numbers by 2. So we should do that. We should take it down to the smallest whole number ratio of the ion. ions. So if you can have a smaller ratio, do it. So that's the idea there. So basically, look at the cation, figure out its charge, look at the anion, figure out its charge, and then figure out how many of each you need to balance the total net ionic charge to 0. So again, one more time, determine the charge on each ion, and then increase or decrease the number of each you have until you have a net charge 0 formula unit. Let's work through some examples. Okay, so if I have lithium oxide and I want to write the chemical formula for that, the first thing you always have to do is pick apart the name, of course. So if I want to write the chemical formula for lithium oxide, again, you look at your ions, you determine the charge on each, and balance the amount of charge you have, okay? So if I have lithium, lithium takes a +1 charge. It's a metal with a set charge. How do I know that? It doesn't have parentheses. It has no Roman numerals. And it's lithium. You know the charge of lithium regardless, so you know that. So one hint is that you don't see the Roman numerals. Another hint is it's literally lithium. So it's literally whatever it is. So you might check out the periodic table, remember that it's in the first column, and so on and so forth. So there are a few different clues you have in your name. So if we have lithium, we know we have Li 1+. Well, if we have oxide, that means oxygen is our anion, right? And we know oxygen, that oxide ion takes on a 2- charge. So I have a cation with a 1+ charge, and I have an anion with a 2- charge. So I need to have 2 positives to balance out my 2 negatives. So I'm going to take 2 lithium atoms to 1 oxygen atom here, okay? So I would have Li2O is how I would write this chemical formula. So I have it here represented on the screen for you. So you might think of it something like this. So remember, our ions are just going to be these atoms or these ions that are attracted to each other here. So they're just kind of hanging out next to each other, that kind of idea. So we know that our lithium has a 1+ charge. We know that oxygen takes on a 2- charge, and we need a net 0 charge. So we would need 2 lithiums so that we had a 2 positive charge. So the subscript on lithium is 2 and the subscript on oxygen is 1, but again, we never write a subscript of 1, so Li2O is the name of, or the chemical formula of lithium oxide. So we also have sodium acetate here, okay? So sodium acetate. So when I look at this name of a compound, I can see that I have sodium in the name. It means I've got a metal, which means I know for a fact I can follow my ionic compound rules. So I see sodium and I see acetate. So I don't see any parentheses in Roman numerals. We know that sodium always takes on a +1 charge. Easy enough. And then we see acetate. Well, acetate's one of our polyatomic ions, of course, that takes on a 1- charge. So I have sodium 1+ and I have acetate 1-. I guess I just need 1 of each so that I have a 1+ with a 1-. They balance each other out, cancel out, so that they have that overall net charge of 0. So our chemical formula is NaC2H3O2. No parentheses or anything in the chemical formula either. If you only have 1 copy of your polyatomic ion, no parentheses. You only use parentheses if you have more than 1 copy of your polyatomic ion. So if I just need 1 sodium ion and 1 acetate ion, that means I have sodium acetate written this way. So again, sodium has a 1+ charge, acetate has a 1- charge. They cancel out really fast, and we don't have to write any subscripts down because they are not, we don't write a subscript of 1. And I apologize, this should be the acetate ion written out here. This should say C2H3O2. However, for some reason, only the O is left. So there's that. So we might think about it something like this. So our acetate is actually kind of a little bit longer of a molecule, a bit more stretched out than what our individual atoms are going to be. So I've kind of pictured it as a longer oval, so it might look something like an attraction like this. Our third example here is going to be tin 2 iodide. So we would say this tin 2 iodide, and we want to write the chemical formula of that. So First and foremost, we look at the cation. We determine the charge on the cation. Well, right away, we know that the charge on the cation is 2 because those Roman numerals represent the charge on one of the tins that are potentially in our chemical formula. So each tin we have is 2 plus. It's not an overall total of positive charge. It's exactly that one tin ion in our chemical formula here has a 2 plus charge. So tin is my cation with a 2 plus charge as denoted by those Roman numerals. And then we have iodide listed as our anion. That's going to be one of our monatomic anions. And iodide takes on a 1 minus charge. So tin has 2 plus, iodide has 1 minus. So I'm going to need 2 iodides to make it 2 minus to balance out my 2 plus from tin. So if I want to write the chemical formula of this one, I'm going to write SnI2. So that might be something that we see here. So SnI2, so each tin ion has that 2 plus charge. It comes from the Roman numeral. And each iodide has a 1 minus charge. We got that off the periodic table, if you will. And remember, we need a net charge of 0. So we need 2 of our 1 minus ion to balance out that total 2 plus charge. So the subscript on tin would be 1 because we only have 1 copy of it. However, we don't write 1. And then the subscript on the iodide is 2. So that would be 2 because we need 2 negatives to balance out our positive. So SnI2, tin 2 iodide. Okay, so we have our last example here. It's one of the more complicated examples, but I have a wonderful feeling that we can handle this, okay? So what is the chemical formula of aluminum oxide? Well, we got to determine our cation and its charge first. So our cation is aluminum. Aluminum is one of the ones we know with a set charge. Aluminum takes a charge of 3 plus. So aluminum 3 plus on one side. We look to our anion. We have the oxide anion. We know that oxygen takes on a 2 minus charge when it forms that anion. So we have something with a 3 plus charge and we have something with a 2 minus charge. So the way I tend to do this is I take whichever one has a smaller amount of charge and I add a copy of that and I reassess. So if I have Al3 plus and I have O2 minus, I'm going to see what happens. What if I have 2 oxygens? Let's just see what happens. So then I would have Al3 plus, and then I would have 2 oxygens, so I would have a 4 minus charge. Well, now I've got more negative than I do positive. What happens if I now add another copy of aluminum? So now in my head I've got 2 copies of aluminum, and I've got 2 copies of oxygen. So if aluminum is 3 plus, and I have 2 aluminums, I have a 6 plus total charge. However, I only have 4 minus from my 2 oxygens. Oxygen is always 2 minus. I've got 2 of them. I've got 4 minus. So I've got 6 plus from my 2 aluminums, and I've got 4 minus from my 2 oxygens. Well, I'm going to try to increase the number of negatives I have to meet the number of positives. So in that case, I would have Al2O3 because I would have 6 positives from my 2 aluminum ions. Each are 3 plus, 6 positives. I would have 2 negative from each of my copies of oxygen. I would have 3 copies of 2 negative. So I would have 6 minus total. So now I've got 6 positive, 6 negative. I have an equal balance of both. So I would have Al2O3. Al2O3. So this is the chemical formula of aluminum oxide. So again, all I'm trying to do is I just kind of think my way through it and I say, okay, if I've got 3 plus, obviously 2 minus isn't enough. I'm going to do that. Okay, I'm going to step my way up. So now I've got 2 oxygens. I'm going to step my way up if I had another aluminum. And I'm going to try to get it so that they balance each other out and I'm taking steps to where I'm even. Okay, so I figured out how many copies of the cation I needed, and I figured out how many copies of the anion I needed so that I had an equal number of positive charge and an equal number of negative charge. So in this case, again, we need that net charge to be 0. So I have Al2O3. Okay, so those are some examples of how we name ionic compounds. I tried to include some pictures down there at the bottom too of how we might think about them. And I've left you with some practice as well. So please, please, please go through, name these, or write these chemical formulas, and see what you can do with that. And then please ask me if you have any questions. Come to office hours, send me an email, we'll set something up. So that is naming and writing the chemical formulas of ionic compounds.